When designing FPGAs into a device, it's a delicate balance between performance, power consumption, and cost. If you underspec performance or use more power than you expected, your design's not going to do what you need it to do. But if you overspec your FPGA, you can very quickly run into budget issues, so it's vitally important to find that sweet spot of performance, power, and cost. So in today's Tech Chat, sponsored by Mouser Electronics, I'm joined by AMD's Romisaa Samhoud to talk about the changing world of FPGAs and their brand new Spartan UltraScale Plus FPGAs. Romisaa, thanks for being here. I'm excited for this.
Yeah, thank you, Daniel, for having me today.
I'm curious, what sort of applications and design demands are driving FPGAs right now?
Yeah, great question. So FPGAs are very versatile. So you can see here some of the key industries where the FPGA really shines. By introducing our cost-optimized portfolio, it delivers the right balance between cost, performance, and power efficiency, which is really critical for cost-sensitive applications. So when you're thinking about AI-enabled ADAS and LiDAR in cars, or medical imaging systems, or robotics, or even 4K broadcast and immersive audio, these are areas where flexibility and low latency matters. And at the same time, in things like video collaboration, keeping the cost and power low is such an important thing. So our cost-optimized portfolio isn't just solving a single niche, it's enabling innovation across a wide range of industries while keeping the solutions affordable.
So when you say cost optimized, I know I've heard the designers I work with talk about like how do I make sure I don't overspec my FPGA and end up with extra, BOM costs and extra, power draw, but also not underspec the FPGA and then have a device that doesn't perform the way they need it to perform, doesn't have the power they need. What makes an FPGA a cost optimized one versus a performance optimized one?
Great question. So at AMD, we offer both. So we do have the lower end, lower side of the portfolio, lower logic density. We also have the latest and greatest high-end products like Versal. So if we zoom out here and look at the bigger portfolio, so we already have a very comprehensive lineup of cost-optimized devices. So on the left-hand side, you can see the older generations like Spartan 6, Spartan 7, RTX 7, Zinc 7000. These have served the market really well for years, and what you'd expect is that they are based on mature nodes like 45 nanometer, 28 nanometer technology. While on the right-hand side, moving to the 16 nanometer, you can see that we have already have a very successful family, like the Zinc UltraScale Plus MPSoC with its integrated hardened processor. We offer also RTX UltraScale Plus for compute and transceiver bandwidth. And what we're doing is we're introducing a new family called Spartan UltraScale Plus that is filling an important gap at low cost and high-end IOs. So it brings the modern 16 nanometer FinFET technology, it brings the lower power and the state-of-the-art security features to the space. So really Spartan here is a natural evolution of the Spartan line, extending the portfolio forward and giving customers the future-ready capabilities with the longer life cycle that they need in this space.
I imagine that a lot of time and effort and planning goes into releasing a new generation of FPGAs. What sort of considerations and what sort of customer requests are you seeing? What are engineers asking for in this latest generation? And how does the lower power and the security really play into the applications that are going to be put into designs now and then deployed for the next potentially 20, 30 years?
I can take an example around why we built Spartan UltraScale Plus. It's really optimized for the edge. So for engineers, they care about the low power, they care about the latest security features, they care about having the transceivers to transmit the data in PCIe. So here you can see that we have a proven technology of the 16 nanometer FinFET, which means that it brings the low power. We also added hardened memory controllers and hardened PCIe, increasing the on-chip so that the engineers can leverage the on-chip memory, and also adding the high-speed transceivers and PCIe Gen 4 with the DSP slices. So what really makes Spartan UltraScale Plus a future ready is that its extremely flexible IOs. We have up to 572 IOs. We have legacy 3.3 volt IOs, which is still really important to engineers in this area, where we're still using the legacy interfaces like I2C or SPI. And when it comes to designing a future-ready product, security is such an important key. So we have enabled our products with post-quantum cryptography readiness. We have features like physical and clonable functions or true random number generators. And we've also leveraged the latest and greatest memories. So we have the hardened memory controllers, LPDDR4X and 5. So that's where the power, performance, security, and footprint comes together, where this FPGA designed to meet those unique requirements at the edge.
It's kind of funny to me to think about having to design like an I squared C bus and at the same time also having PCIe Gen 4 like a by 8 system. Those are just such snapshots of points in time and technology, and it makes sense. You know, so many sensors run on those things and other items. So it's just kind of a funny snapshot and juxtaposition to have those two together on the same
Yeah,
FPGA.
yeah, of course, it's very popular. Like, still, we see a lot of designers have requirements around the legacy 3.3 volt support, and that's why we are still having them supported in our devices.
So hardened memory, is that like rad hard for space applications, or what is kind of who's asking for hardened memory?
Hardened memories is it's not just for space, it's basically taking instead of customers implementing the memory controllers using their logic density, their FPGA resources, they have it hardened on the chip itself, so they no longer need to consume their logic resources to implement a memory controllers to control their memories, basically. And that is an area that is very critical because you don't want to end up, like you said in the beginning, you don't want to end up into larger FPGAs to meet your requirements. You want to be in the right amount of logic, right amount of features that you're looking for so that you don't overspend, where you get the right fit for your application. So that's why it's very critical to have a support for memory controllers that are hardened, where customers can leverage those for their application with peace of mind about like not using logic to implement them.
And I want to talk about post quantum security in a moment, but I'd love to dig a little more into the geometry node and how the FinFET architecture. So, can you talk a little bit about the technology node that was used to build this latest generation?
Yeah, so we are using the TSMC low power, high performance FinFET process node, which is basically what does that means for customers? It means two things mainly. It means the low power and the high performance. So if you look at the chart here compared to Spartan 6, our Spartan UltraScale Plus here offers up to 60% lower total power in terms of the static and dynamic power. And even against the most recent 28 nanometer like Arctic 7 FPGAs, it still brings up to 30% lower power consumption. So that's one particular area. And importantly, like this isn't just about saving power, we're also doing that while offering high Fmax. So customers can get both more efficient operations and the ability to hit high clock rates, speeds. And that's why Spartan UltraScale Plus is a very strong choice for edge and cost sensitive applications where you don't just compromise between performance, but you also compromise in power at the same time.
Can you talk to me a little bit about Fmax as a spec? What is it? How much should I care about it as a banner spec versus looking at the other sorts of capabilities I need out of an FPGA?
So Fmax comes when you start designing for performance. So as an example here, we have up to 40% better utilization because of our architecture with the LUT6. But the Fmax here is that we deliver up to 1.8x more frequency headroom, which means that you can drop down a speed grade, reduce the dynamic power, but still outperform the competition with this product, which is a huge win to the cost-sensitive applications. So it's mainly like running your design on a faster clock rates while also preserving power with the 16 nanometer FinFET technology.
So essentially, it's not necessarily what is the fastest FPGA I can possibly find, register switching frequency. It's how much processing power do I need, and what amount of time, and can I accomplish the tasks I need without breaking my whole BOM budget on the
Yeah.
latest and greatest, biggest FPGA.
Yep. That's a great way to put it.
Let's talk a little bit about power consumption. How you've mentioned dynamic and static power. I can assume that static power is essentially just like rest mode, sleep mode, but it's not working hard in dynamic. Is that like the peak power, the most power it could possibly consume at once?
So the dynamic power is the power that is consumed during the running of the FPGA. So it's basically the power that is used for all the building blocks inside the FPGA. While the static, as you said, it's basically the sleep mode of the FPGA without really running blocks here and there.
What sort of challenges or advice do you have for people who are planning the power budget for their system and they're trying to spec batteries and spec, the other energy type devices in their systems? Any advice or things to watch out for as they start to plan that power budget?
We do offer a PDM tool for customers that they can use in order to measure their power and start adjusting how much resources they are going to utilize. So that's a great starting point when it comes to setting up for your next gen products. You start with the power measurements, and we have a dedicated tool for that.
So, as people are going to start specing an FPGA for their design, what sort of parameters and things do they need to know about their requirements before they can actually choose the right FPGA for them?
Let's start with an example here. So this is the full family lineup. So you can see how it scales across different application spaces. On the left-hand side, we have devices like SU10, SU25, and 35. Those are a great fit for IoT sensor hubs or small robotics controller, for example, they are really tiny, cost sensitive, but also have tons of IO flexibility. And we're industry highest IO to LC ratio for these devices compared to 28 nanometer and lower nodes. So those parts gives you the flexibility of IOs in small form factor like 10 by 10, which is perfect for space constrained edge applications. And as we move to the middle densities here, like devices like the 45, SU45P through SU65P, those can better serve applications like baseboard management controllers, where this is shown up in servers, telecom systems, and industrial equipments, where you need more memory, more hardened interfaces like DDR and PCIe, and the reliability to manage larger systems. On the right-hand side, we have the larger devices like SU100P, 150P, 200P. These are heavy lifters where you can get the larger logic cell density, wider on-chip memory with the support of the UltraRAM that we have added, and transceivers. So those can fit into applications like edge AI vision systems, advanced medical imaging, or even industrial automation controllers. Those do not just handle IOs, but also handle the local compute and signal processing applications.
So, if you're putting a device on the edge and you want it to maybe run some AI ML stuff or do some processing before it's sending that data out into the network core, you would potentially need a bigger, stronger FPGA. But if you're deploying this maybe into just a robotics arm to do some, custom applications, you could potentially get away with a smaller one with less processing power and less I/O.
Yeah.
So let's talk about I/O for a moment. We all like, more I/O is better, but there's always an engineering trade-off there. What should people be thinking about as they're trying to match up, their I/O with their processing power, and what sort of applications does this make sense for?
So for a product like Spartan UltraScale Plus, you're looking for the I/O flexibility in order to connect to everything from modern high-speed links to legacy 3.3 volt interfaces, all of that within a single device. So for the smaller Spartan UltraScale Plus devices, the story here is about the I/O expansion. So these are perfect for baseboard management controller applications, like in data centers where you can need to connect to CPUs, GPUs, power systems, and sensor efficiently. So we here offer up to 3.5x I/O to logic cell ratio compared to the previous generations. and you get unmatched density for IO-intensive designs. While on the right-hand side here, on the higher end with the portfolio, we can shift here focus into connectivity. So thinking about industrial robotics, where you have motors, cameras, and sensors, all of them have to talk to each others in real time. And we here offer up to 2.5x the transceiver bandwidth and 4x the MIPI bandwidth compared to previous generation RTX 7 and Spartan 7 devices. That is enabling seamless edge sensing and control.
So let's talk about banks for a moment. I know there's kind of different types of banks you'd use for different applications, and these things have flexibility there. Can you walk me through some of the most common types and then what's new or different about the next generation?
So when it comes to the IOs here, just like lining up the different IOs we support across different generations, so comparing Spartan UltraScale Plus to the UltraScale Plus and Versal in terms of the IO, you can see here that Spartan UltraScale Plus supports three different banks types as HDIOs, HPIOs, and XP5IOs, offering the balance between higher voltage flexibility and higher speed performance, as well as the dedicated memory support. We have up to 1800 megabits per second data rates, and Spartan here stands out by combining the broader I/O coverage for HDIOs with the high-speed features of HPIOs and XP5IOs, giving designers the flexibility for both expansion and performance-driven application. And also taking a look at the I/O features across the HD, HP, and XP5IOs. The HDIOs here stand out to be the broader voltage support up to 3.3 volt, which makes it ideal for legacy interfaces like I2C, SPI. Meanwhile, the HPIOs and XP5IOs bring advanced high-speed capabilities such as serialization, deserialization, and robust signal integrity features, enabling the designers here to choose between legacy compatibility and cutting-edge performance.
So you can kind of essentially mix and match your banks and like mux them into your input output pins.
Exactly. It really depends on what you are interfacing with, what is the capability that you're looking to achieve.
Any advice or things people should watch out for as they're trying to spec an FPGA into their device, like things you see people run into or things that they should pay extra attention to make sure they get correct?
That's a great question. I think security here is a key. It's not just a feature anymore. Security, it's more of the foundation of trust. So whether it's protecting the IPs or authenticating devices or future-proofing against quantum threats, we need the FPGA to bring the state-of-the-art security features into the cost-optimized portfolio, and that's what we are achieving with Spartan UltraScale Plus.
So we got to then talk, as quantum computing is on the rise and potentially getting RSA broken down the road. Let's talk post-quantum security. Who's it for? Who cares about it? And what does that look like?
So why post-quantum cryptography matters? It's, as you said, the quantum computers poses here a serious risk of today's encryption by potentially breaking through long-term confidentiality and authenticity, which is why the US government released a new quantum resistance algorithm requirements back in 2022. And we're seeing a phased rollout under the CNSA 2.0 timeline with the new signature schemes like the Layton-Macaulay signatures, the XMSS for firmware, symmetric algorithms like AES and SHA are still remaining strong, and a new asymmetric standards like the crystal Kyber and the crystal dilithium, ensuring the future proof security.
So there's a whole post-quantum cryptography side of this conversation, but if we take a step back, who cares the most about security and what are the downsides of maybe having subpar security?
Almost the majority of our customers pays quite good attention to security features. Our main goal here is to help customers achieve three main things. We want to help them to protect their IP, prevent tampering, and also maximize their uptime. So taking it here to focus on the IP protection, the post-quantum cryptography support, the AES GCM for secure configurations, and the physical and clonable function, making each device unique. Second is preventing tampering with the customizable permanent tamper penalty that we have in order to protect the device against any misuse for the security features, and the DPA countermeasures for side channel attacks. And third is maximizing the uptime of their products, which is by enabling these SAU performance and increasing it from the previous generations, but also giving customers the flexibility to have an in-field upgrades for temperature and voltage monitoring. So those are three main goals we have in order to help our customers maintain their secure features within their FPGA.
What is the role of like in-field temperature and voltage monitoring? How does that relate to security?
You want to make sure that you can have an in-field upgrades to your FPGAs without breaking into any security features, without having any tamper done on your FPGA. So that comes with a secure booting and the in-fields upgrades here for the FPGA.
And obviously, infinite security at infinite cost is not helpful or viable. So there's always some level of trade-off between cost and performance and security. What sort of things does AMD think about, and what are customers asking for as they start to, prioritize different parts of the kind of security web that they have to, kind of security menu they have to pick from?
So for security goals here, I think the priority is to ensure the confidentiality and authenticity while protecting the customer's IPs against today's and tomorrow's threats, including the post-quantum risks. Some key use cases here to ensure a trusted systems are the system startups with the secure boot to safeguard sensitive data through secure off-chip storage, and also to protect the system integrity with the secure debug controls. Additionally, we have a platform firmware resiliency to defend against the firmware attacks. And together with the built-in FPGA features, these delivers a strong physical and logical security while balancing the cost, the performance, and the power.
I think you brought an example, also kind of a mock-up of what a secure setup might look at. Can you talk me through that block diagram?
Yeah, so that's about the platform firmware resiliency. So taking an example here on a use case for platform firmware resiliency, so you can see that Spartan UltraScale Plus here established the root of trust during boot, ensuring the firmware is authenticated and protected, where we have flexible I/O support that interfaces with I2C, SPI, and enabling the protection, detection, and recovery. So the system can be validated for the integrity, detect the corruption, and restore the firmware securely. Within the FPGA, we have built-in cryptographic accelerators available for post-boot, so designers can save resources, reduce the swap-C, size, weight, and power, and cost, and also accelerate the time to market compared to implementing these features.
I have maybe some like nightmares still from my undergrad trying to get my FPGAs programmed in those double E labs, but I'm blown away by how far some of these tools and workflows have come. What does it look like today to design and work with FPGAs from like a software and toolchain environment?
That's a great point here. So we have the Vivado design suite, which empowers developers with the industry-leading capabilities for design, debug, and optimization. So Vivado here is not just a tool, it's basically a critical enabler for productivity. It enables faster time to market and successful deployment for our FPGAs. And a quick good example here to focus on how Vivado simplifies the design process. Traditionally, design flow are fragmented for other vendors, relying on multiple third parties tools for simulation, for synthesis, place and route, and debug. So each has its own license, its own training, and its own support challenges. So that's not an ideal case for customers. But within AMD, we have the Vivado suite, which have a unified approach with a single end-to-end tool offering a streamlined flow, dedicated support, and also reduced total cost of ownership. So we are focusing on helping teams to move faster with less complexity and less dependability on multiple vendors.
talking about routing and synthesis and making sure you're not getting too much crosstalk and your clock trees and timings all work out well. Can you talk me through a little bit more how timing is important and how that plays out for the Spartan line?
So AMD has a clear advantage in timing closure here. On the lower end, once the designs run above 100 megahertz, AMD devices already show stronger timing consistency compared to other competitors in this area. By the mid-range devices around 200 megahertz, we still maintain a significant lead and almost closer to 100% of design meeting timings, while competitors rapidly falls off. This means that engineers spend less time wrestling the timing issues, achieving faster design closures, quick time to market, and ultimately faster revenue, all while benefiting from the better efficiency at lower voltages.
So having timing is obviously critically important, but when you look at performance, it's tempting to just look at how fast can I crank up my clock, but really performance is more than just how fast your clock is ticking, right? There's other things to think about.
Yeah, so we have an advantage here at delivering superior performance at lower speed grades. So compared to the competing 16 nanometer devices, you can see here that AMD offers up to 1.8x higher Fmax, which means that you can often step down a speed grade while still outperforming the competition. In fact, here our slowest speed grade, the Dash 1 LV device, outperformed the competitor's fastest speed grade, giving customers a clear advantage in performance, in efficiency, and also design flexibility. So now pivoting from showing our technology advantages, the benchmarking, and focusing into the practical steps that customers can take to work with Spartan UltraScale Plus. Here you can see that customers can get started right away. So we have the smaller products in production already. We have the tools, we have the documentation, the silicon sampling, and the devices available in production. So all of those are already available. We are also forward looking here to a new milestone, which is the evaluation kit arriving in Q4 of this year. So that can give the developers the opportunity to accelerate prototyping and deployment within an evaluation kit offered by Spartan UltraScale Plus.
So it must be incredibly exciting for you and for AMD to see this new line coming out. If I were to implement one today, how long could I expect to be able to use this in my devices? Do I need to worry about end of life or anything like that?
I think AMD have done a really great job at doing life cycle expansion. So our average life cycle is 15 years. As you can see here, we tend to go way above and beyond this timeline. So for example, we have done some couple of life cycle expansion to our 45 nanometer Spartan 6 to 2030, our 7 series, including Arctic 7, Spartan 7, Zinc 7000, and Kintex and Vertex 7. Those are going to be available through at least 2040 plus. And the next generation Spartan UltraScale Plus, that's based on the 16 nanometer FinFET technology. We achieve a very higher span with this node here. So with availability at least until 2045 plus.
So this is going to outlast me in the industry, is what you're saying. So an incredible device and an incredible line coming out. Can you kind of recap for us some of the things that you are most excited about for the Spartan UltraScale Plus?
Yeah, I just wanted to take this opportunity to wrap up the value of Spartan UltraScale Plus here in three key areas. First one around the features, so the high I/O, the low power, and the strong security features. With the industry-leading I/Os density, we also have up to 30% power saving and more power saving with our hardened interfaces as hardened memory controllers and PCIe, and the most comprehensive security features within the cost-optimized portfolio, including the post-quantum readiness. Second here is focusing on the productivity and how the tools can enable customers with the accelerated time to market. So thanks to Vivado design suites, it's unifies the flow from simulation to verification, and you also have the support of all the 20 nanometer and smaller node within the same tool. Finally, the trust and longevity. So AMD brings 40 years of FPGA leadership. We have billions of devices shipped. We have over 15 years of the product lifecycle support, ensuring customers can design once and rely on us for the longer term availability.
Well, this has been fantastic. If someone wants to look at implementing one of these into their designs, where should they go? Who should they talk to?
So we do have public web pages to start with about the product. We also have public documentation that customers can start using today. For the device shipments and everything, we advise customers to work with sales, and also at the same time, we want customers to start using the tools themselves and start evaluating the product. So just by downloading the Vivado, what's unique about Spartan UltraScale Plus is that, and also all the cost optimized portfolio is that it's supported for the free standard edition of Vivado. So customers don't need to worry about any licensing or payments or around the Vivado tools. So they can just download the tools and start with it today.
So they can get started in Vivado right now for free. That's fantastic.
Yeah.
Romisaa, thank you so much.
Thanks, Dan. It was great having this discussion with you.
Thanks for tuning in to this Tech Chat brought to you by Mouser Electronics. That was AMD's Romisaa Samhoud, and Mouser is an AMD authorized distributor of Spartan UltraScale Plus and more, so check those out at mouser.com. I'm Daniel Bogdanoff. Thanks for watching, and I'll see you next time.